We'll go ahead and get started. I know there have been some questions/concerns about what the exam will look like, so I thought I would give you a sense for that. I'm going to try, I've never done this before, but one of my important goals for you is to make sure you can think on your feet when answering organic chemistry questions or proposing hypotheses in response to experimental data. So I want to try doing our first exam in an oral format. And what that's going to look like is at some point before your oral exam, I will give you a list of questions. And I will tell you you need to pick two or three, I'll say we'll discuss two or three of these one-on-one, and you can pick one and I'll pick one. So you'll have some time to prepare, and then you'll either come to my office or we'll have a meeting via Zoom, and you can talk me through your answer to the problem. And I will score your answer based on this overall rubric, which I'll make available on Learning Suite, but you'll be scored in areas of understanding, or your answer's fully developed and based in MO or valence bond theory, or your answer's clear and coherent, are they reasoned and error-free, or if you screw up, do you catch yourself? Are your drawings good, easy to read, good to interpret? When you're communicating, it helps when you're communicating if your drawings are not unintelligible. And then prompting, do you need me to lead you down the primrose path to get the right answer, or can you arrive there on your own? Each category is sort of scored from 4 to 1. What does that mean? That roughly correlates with like A, B, C, and D, roughly. I'll give scores in half integer values too, if you want, and I haven't decided whether we'll weight each of these categories differently. Out of how many points is this? Well, there will be a point total, and this will be worth what I said in the syllabus a midterm exam would be worth. Okay? Yes, Kim?
Two questions. So number one, what are we allowed to use in preparing to come to your office?
That's great. What are you allowed to use preparing to come to my office? Obviously, you can't ask me questions once you have the exam. Dr. Price, can you tell me the answer, and then I will tell you the answer back. So I'd like you to work alone because I want it to represent your understanding. Your resources can include your class notes, the textbook. You can use the internet as a resource to learn things. I don't want you to log on to websites that offer to take your homework and do it for you and then give you the answers back. Probably not, I just had this experience in one of my 351 classes last time. So, I trust you guys. We're all friends here. And in any case, even if you try to cheat, you're going to give me your answer, and by then you need to know it and understand it. How would you guys feel about needing to give the answer to me without notes? You don't have to say anything now. Mostly, I'd like to know that you understand it. So I don't necessarily want written. I don't necessarily want you to just read it to me from a sheet of paper. Nevertheless, I use notes when I'm teaching, so I think that just answered my question. All right. Logistically, this may be a bit of a challenge because you guys are busy. I am less busy than you. I just work in my office on things I'm interested in, so it's fairly flexible in terms of schedule. I'm thinking Thursday probably as a day, or not Monday, Wednesday, Fridays better for folks.
Oh, isn't as in it's happening next Thursday or a
Yes.
Thursday?
No, next Thursday. So what we'll do is, what's the best way to do this? What's that? Yeah. Yeah, so I'll let you guys know in an email what times are available, and you pick one. If you're remote and or quarantining, that's fine. We can do this over Zoom. You could, you'll maybe, I don't know, have to be creative, but if you put your camera somewhere over a sheet of paper, that could work. We can figure out a way to do this remotely. And I'll deliver the exam to you remotely as well. Just email it to you and you can look at it. And I think I'm going to give you probably 24 hours to prepare. So I don't really want this to be a 5-day horrible thing. 24 hours before your appointed time, I will send you your exam. Is that? Or do you want it the morning of? That'd be awesome. No? Okay. I don't want this to be a nerve-wracking experience. Most of you know me, and I'm not a jerk most of the time. So, yeah, go ahead.
Can we have 48 hours just because, like, my Monday, Wednesday, Fridays are insane, and so if I'm like...
Okay, can you have 48 hours? Yes.
I'd like to be able to work on it on Tuesday if I'm...
Okay. Yeah, you can work on that. You can work on it on Tuesday. Yes. Any other concessions you want to get from me?
Are we going to get points for our reading questions?
Yes. I think I already posted the answer that you did it for chapter 14. Most of you probably didn't notice it. So what I'll do is by next week when the test goes out, I'll also make those things available. Okay. We're not going to do a problem set per se. Yeah, I had intended to have some kind of practice exam or problem set. This format, you're sort of getting the exam as a practice exam and then you're performing for me. We can talk about whether it might make sense for you to submit your written answers as well as your as well as the oral exam, but that's sort of what I'm envisioning.
Yeah. If there is a quiz, it's not published yet.
Okay. All right. Sorry about that.
That's all right.
And is that quiz just like check yes, you did it?
Check yes or no. Yep. Yes, I did it. No, I didn't do it. And you get the points no matter what. Anything else? Adam is our TA, and you can ask him questions, though he cannot do the exam for you. Can you ask other persons
Yes.
in the class?
No, in the class, outside the class, for trying to resolve the problem.
I want it to be your own work. Okay. All right. So we'll, but by Tuesday I will have an exam for you. All right. So today I think I want to finish up on chapter 1 with molecular orbitals. There's a few sort of interesting stories we want to tell. There's some stuff in chapter 1 that we won't have time for. For example, the description of anions and the fact that they can invert the description of radicals and how in most cases they're not actually planar, they're pyramidal, but the barrier to inversion is not high. We're going to spend today talking about cyclopropane, carbocations, and then non-classical carbonium ions, which are kind of fun and have applications in terpene biosynthesis and the biosynthesis of cholesterol. So cyclopropane is an interesting beast. because, and you're probably used to thinking of it, I don't like that triangle, as highly strained. If you look at this from a hybridization point of view, you would conclude that the bond angles here are substantially distorted from tetrahedral geometry. And so you might expect that you don't have exactly end-on-end overlap of sp2 hybridized orbitals or sp3 hybridized orbitals making those carbon-carbon bonds. And some people have described cyclopentane as having so-called bent bonds. We're going to think of this in another way. We're going to imagine bringing 3 of our bent CH2 groups together, mixing those group orbitals to get MOs for cyclopropane out of it. So let's remind ourselves what our alphabet for bent orbitals is. For bent CH2, sorry. Okay, you've got that low energy all S sigma type orbital. Then you've got a pi type orbital that looks like this with a phase change at carbon, sort of horizontal node from our perspective. You've got a second degenerate. Am I thinking about this right? Oh, then you've got the sigma out orbital. And then what would be left over at that point is the unhybridized p orbital. And that unhybridized p orbital is going to be coming out of the page and back into the page. All right, so that should look pretty familiar. Those are sort of the 4 group orbitals you have from planar bent CH2. All right, so we're going to bring those together and we're going to imagine mixing 3 of these together in all possible phase combinations. And we'll do the same thing here, the same thing here, and the same thing there. All right? So the lowest energy one is pretty easy. I'm going to draw these orbitals from above, superimposed on this structure. So let's call this sigma, pi, sigma out, and p, just to simplify our discussion. So this is going to be the combination of the 3 sigma orbitals. You're going to have one that has them has all of the s orbitals in phase on all of the atoms. And that's the boring one that's easy because it's just one huge cloud of in-phase electron density across all of the atoms, and that's always going to be the lowest energy one. The size of my circles there doesn't mean anything. I didn't mean to communicate that it was smaller on that carbon. So this is going to be, of our options, this is going to be a lower energy one. And then we're going to have 2 higher energy ones. And in a lot of ways, this is going to resemble our allyl type system. We can do this so that you have these 2 on the bottom in phase and the one on the top out of phase. but there's also the possible combination where these two would be opposite in phase and there would be a node going through the third carbon. And these orbitals are carbon-carbon antibonding in a sense, though they are still carbon-hydrogen bonding character. So these two would be degenerate. All right, and we can check our work by going over to Spartan and deleting everything and then drawing a triangle. It's an ugly triangle. Spartan cleans it up for us. There's the lower energy orbital we predicted. There's the one that looks like the one on the right. And then degenerate is the one where there's a node in the plane of this one of the CH2 groups. Okay? All right, so, and remember in the MO picture, we're losing track of what the actual bonds are because 2 electrons are delocalized across the whole molecule in each orbital. The pi approach is going to look basically exactly analogous to what we've done here, only there's going to be a node in the plane of the ring. And I'm deciding to be nice by not just copying these 3 and then drawing lobes below, because that would seem mean. So we're going to have p orbital coming out and then back into the board as we've drawn it here. The lowest energy option will be for these 3 p orbitals to be in phase. And then we'll match the phase on the hydrogens with the part of the p orbital that they are closest to. So the down hydrogens will be yellow and the up hydrogens were going to be pink. This is what we get by combining the 3 pi type orbitals. Okay, and if we were to look at that in Spartan, what we would basically expect is a cloud of electron density above the ring and one below the ring, a pi type orbital. Okay. That's kind of awesome because you would not have looked at cyclohexane and said, oh, there's pi character in that molecule, but there is. And if we look at Spartan, we can see it. There we go. There is our pi type orbital. It's pi type in carbon-carbon bonding character. It's got a lot of sigma, or, well, I don't know how I would describe it. So I withdraw the comment. Questions so far about what we're doing? Okay. So similarly, we're going to try 2 here on the bottom that are in phase with each other and 1 here on the top that's out of phase. And we'll line up the appropriate hydrogens. These 2 will be yellow on the bottom with yellow down hydrogens. There's a node in the middle, and that's a yellow up hydrogen. And then our other option, exactly analogous to what we did above, is going to be to have these 2 on the bottom be out of phase with a node in between. And I'm sorry, I guess if I wanted to keep things consistent, I should have controlled what went where. Oops. Somehow it's bothering me that these kinds of orbitals are there. So we're not necessarily at this stage worrying about the relative energies, about the exact energies, or who overlaps with what? Only that in each combination we've got a lower energy orbital and two degenerate higher energy orbitals. Go ahead.
So maybe this is just me thinking about nodes wrong. When I look at that far right thing, I see, if I were to rotate it, it would look like the one on the left, and if you see what I'm saying, like if I were to rotate it around.
Okay, yes.
Like,
Okay.
then we have yellow, pink, and I'm like, shouldn't this be a node? Am I just thinking about how nodes are created wrong? Because I'm like, it would
Okay,
be
so
out of phase with that, in phase with that, so no orbital.
Kim is saying that shouldn't, if thinking if you rotated it this way, it starts to look a lot like the one here on the left, where there would be a node here, and why doesn't that node go through the hydrogen on the top? And that is a fair question. You arrive at this answer basically by mixing the orbitals first two and then the third. So we would imagine going through this conceptually. I'll erase what we've gotten here to help with it. We're dealing with, and maybe for our discussion we should finally number the carbons 1, 2, and 3, if that's okay. So we start by just mixing orbitals on 1 and 2. We're mixing the pi-type orbitals, and you've got in phase versus out of phase, right? And I guess we would have to do that yeah, so we start with just two of them. There's only two different ways to do it. You can do in phase or out of phase. Then we're going to add the third. If we add the third one in phase here, we get our lower energy option. If we add the third out of phase to the first combination, we get this option that we drew previously. Because we started with these two being out of phase, there's a node in between them, and there can't be anything on that second carbon. Technically, the node for the orbital to our right goes sideways through the molecule. And so this node is not along a mirror symmetry line, whereas this one is. That's qualitative. I think it's unsatisfying, Kim, because you're right. Why don't I just slide that node over and then it's the same thing? And I guess I don't have a good answer for you other than that those are the wave functions that come out of the Schrodinger. Go ahead, Michael.
When we usually draw nodes, are we supposed to have it equal? Usually, when you divide the node, like with benzene, we usually divide it by, I don't know.
Okay, when you have a node, don't you split the molecule in even parts?
Yeah.
That sounds good. Let's see whether the actual picture is different than what I've drawn here, because if the math says something different than I've drawn, then this is an easy problem to resolve. All right. So that's our out-of-phase pi-type option. And that's the other one. And yeah, the node... I don't know why it doesn't let me rotate. I want just a about the z-axis rotation. It's not giving it to me. All right. So yeah, the node here sort of swings. It's like a node surface. And yeah, and there's no reason you can't do that. I think perhaps the reason it doesn't do that in benzene is because you have an even number of carbons. Yeah.
So if I was looking at that molecule, I wouldn't be able to tell the carbons apart because it's perfectly symmetrical.
Right.
So or is it like spread out over all three because you can't tell which one's which?
So that's a fabulous question. And Austin, I think you asked that at the end of class yesterday with respect to benzene. And the question is basically, this is a symmetric molecule. Carbons 1, 2, and 3 are equal. Nevertheless, in this picture, carbon 3 has a node on it. Does that mean carbon 3 is qualitatively different from the other two? Well, no, it can't. How do you resolve that question then? What am I going to say? Well, my guess is that if you put electrons in all of these orbitals and then calculated wave functions squared at each and every carbon in the molecule, you're going to get the same answer. What I don't know is something Austin asked, which is that node permanently on that carbon, or does it switch to go through the other one and switch to go through the other one? I really have no idea, only I think in many cases we're dealing with the time-independent Schrodinger equation, which means we're looking at it as a snapshot. But you are right. All the other options have to exist as well. And I'm thinking it's probably something, do you remember the Pauli principle from chapter 14, where actually each orbital is not occupied by a specific electron, it's occupied by part of a specific electron, contributing to all of the orbitals. And there may be something like that going on here. I'm sorry that's not, that's a terrible answer, but I did look up your question. I tried to Google it very specifically, and I got nothing. So you're asking good questions, and Michael, go ask Dan. Dan knows everything. So, all right. What else? Okay, here's where it gets fun. Well, fun. We're up to the sigma out combination. So let's mix those three together. Oops. Fun. I'm making mistakes. Delete. Paste. Paste and paste. So for the sigma out combination, what we're going to do is all the hydrogens are going to be in phase. There's going to be a lobe on the back of the carbon, and then you're going to have the three sigma out lobes actually pointing not along the bonds, but I think we decided that those were going to be yellow, toward the center of the ring. So this is a weird kind of end-on-end overlap. These orbitals are not aligned with the bonds, but are rather pointing out into the center of the ring. And you'd predict there would be substantial electron density in the middle of the ring. And in fact, there is. And that makes this sigma out type orbital quite a bit more stable than the two upper pi type orbitals. This looks like, got any Star Wars fans out there? Back when I was a teenager, and also probably 6 months ago, I was playing a game called TIE Fighter, developed by Electronic Arts and Lucasfilm, and you could fly a TIE Fighter and be a bad guy. There was also an X-Wing one, but TIE Fighter was just awesomer. And there was a ship called the TIE Defender, which was trifoil instead of two of those wings, and it was an awesome ship. And this reminds me of the TIE Defender. So, okay. Sorry. So that's the TIE Fighter orbital. we're going to do the same thing we've done above with each of these sigma out orbitals. We're going to have a combination that puts a node through carbon 3. And then we'll have out of phase lobes here and in phase lobes here. So that would be our sort of one of our two degenerate higher energy ones. Oh, wait. No, that's right. And then the other one would have these two still oriented to the middle and still in phase with each other, whereas the third one is out of phase. So, yeah. Okay. And yeah, so those are our 3 sigma type orbitals, but the picture is, the pattern is the same. You got 1 lower, 2 higher, and one of them is going to have a node through carbon 3. We can actually look at these. These are not, oh, are they? Those are the pi type orbitals. So these two are actually, hold on, Joshua. Oh, that's the area of confusion. These are substantially antibonding in a direct end-on-end approach, and that tends to be destabilizing. So we wouldn't necessarily have predicted it, but these are not bonding orbitals overall. They are overall anti-bonding. And so they're going to show up. That's why they don't show up on Spartan. I was looking for them and I didn't see them. Okay. So lastly, we've got the p orbitals, and this is where it gets even more sort of strange, because not only are you dealing with p orbitals that aren't even kind of oriented along the axis between atoms, but p orbitals have plus and minus character, and this is in a ring. This is in a ring. They're oriented to each other. So it's really hard to determine what an in-phase combination is versus an out-of-phase combination. So we might try pink here, pink there. Once we've made that choice, it has to be yellow here and yellow there. We can't complete the ring with a completely bonding interaction. There's gonna be a node. So I say let's pick here and there. All right. So that's one possibility. That's the best we could do. Your text calls this arrangement of p orbitals in a circle where you can't get them all to line up as Mobius topology. Mobius, you remember the Mobius strip where you take the sheet of paper, you bring one twist in it, and you put it together, and now it just has only one side. Nobody knows what I'm talking about. Okay. For those of you playing along at home, I am now ripping a sheet of paper to demonstrate Mobius topology. Okay, so if I bring it together like this, it's a two-sided system. Everything lines up. I can twist it though, and now I can go from one side to the other without ever. Okay, that's irrelevant. And the Mobius topology thing is kind of irrelevant. Anyway, it just means that you can't, it's not like benzene where you can line the p orbitals up and they can all be in phase. Sorry. Failed demonstration. Another option we can consider would be to have these two on the bottom in phase with each other. Oops. And then it's not totally clear what to do. And actually, your text I'm sorry, the calculations show something weird. So we'll just go the option you saw there is kind of this one. All right, you have a node running through the molecule, then you have a lobe here, and a lobe there, and then you have lobes in back of those carbons. So if we go to Spartan and look at it, that's sort of what we're seeing there. The other one is a little tricky. You can sort of see in our drawing in Notability, we had a p-type orbital going this way on carbon 1 and one going this way on carbon 2. I don't know where you get the lobe on carbon 3. It's not at all clear where that one comes from. But it's there, and so I'll draw it. That one would be hard to come up with, and I don't think I'd expect you to do that. And then there would be a higher energy out of phase one. But these two, which we haven't drawn, dang it. Thank you. The higher energy out of phase one and I don't know why I'm drawing it lower to make in our drawings to make things confusing. That would be to have as many out of phase options as you possibly could. So you put them arranged, oriented all the same sort of clockwise, and you get the maximum number of nodes. So these, interestingly, because of the weird shape of the p orbitals, whereas before we've always had one lower energy orbital and two higher energy orbitals, the way the p orbitals are, we now have two lower in energy options and a higher energy option. And these end up both being the HOMO, the highest occupied molecular orbital for the molecule. So, what does that mean? Go ahead, Austin.
So I'm looking at the right HOMO, the one with the weird
Yeah.
Orbital that we can figure out.
Yeah.
Could you get that from adding in one of the sigma outs that were higher instead of using a p orbital on it? Like the sigma out from the top
Yeah,
right
could
and
you get that one by adding
like
a
from
sigma
like,
out there?
Yeah, like the one we have on carbon 3 on the rightmost sigma out.
Yeah, that's interesting, and that may be where it comes from. I don't know.
And are you allowed to just mix in natural orbitals like that?
You're allowed to do whatever as long as you get the same number of MOs out as the atomic orbitals you start with. So that's good. Yeah, conceptually, I don't know where that one comes from, and I don't think your book actually talks about it. The point to make, though, is that the HOMO of cyclopropane has substantial pi character coming out of in the plane of the ring, but outside of where the bond is. Okay, and this creates an interesting situation. If you want to, let's see if we want to demonstrate what this orbital looks like. I'm just going to show you. It creates this situation where the highest energy orbital of cyclopropane has pi character. And looking over at Spartan, we'll look at that one. It's almost like you got a pi bond there, right? What do you think might happen if instead of a hydrogen on carbon 3 there, what if I had a carbocation, a CH2 group? what would that look like? Let's take this option as an example. Uh-oh, warning, the answer appears below. We never have enough time in this class. Needs to be a 3-hour class every day. Not funny. Okay, so imagine taking this hydrogen on top and instead making it be a carbon. And let's have it be a carbocation. Can you envision a situation where the p orbital on that carbocation could line up in phase with the pi orbital on the orbital with pi type symmetry in cyclopropane? Okay, yeah. And in fact, if you do the calculations for cyclopropyl carbinol cation, you get essentially that answer, okay, where the electron-rich lobes from the HOMO of cyclopropane are now mixing with the p orbital on the positively charged carbon. This ends up being the HOMO of cyclopropyl carbinol, and we can get the LUMO of cyclopropyl carbinol simply by taking that p orbital and switching the phase. So what this tells you is that when you put a carbocation adjacent to a cyclopropane ring, it is kind of like having a pi bond next to it. Okay? Remember that a pi bond next to a carbocation allows formation of an extended pi system in our valence bond theory language, where the positive charge is delocalized and the LUMOs on atoms 1 and 3. When you put a cyclopropyl adjacent to a carbocation, now that LUMO, that what we would have thought was the empty p orbital on that carbon, is also on the carbons of the ring, delocalized there. Okay? So this has some interesting consequences for reactivity. What it means is that cyclopropyl carbonyl cation is unusually stable, at least stabler than we would think, more stable than we would think a primary carbocation would be. Because it's not a primary carbocation, that positive charge actually ends up being delocalized. And this can explain some funny behavior we see with cyclopropane rings with positive charges adjacent to them. They are known to rearrange. So I'm going to redraw our cyclopropyl carbonyl. I'm not sure how to do this. Maybe from the side would be better. Who knows? All right, so here's a hydrogen coming down. Here's our positively charged carbon. And remember that on that positively charged carbon, you have lobes on the p orbital overlapping with lobes associated with these carbon-carbon bonds. These are known to rearrange to alternative structures. Want to make sure the way I'm drawing it sort of does it justice. So it's actually easy, and what the way we would draw this in a valence bond sort of type way would be to actually draw sort of resonance structures That's not meant to be 1, 2, 3, 4. That's a four-sided thing. Where now this carbon is positively charged. And we can also rearrange it further. So that these electrons come here, and now we have the positive charge out on that carbon. And it's been, in some cases, an open question in organic chemistry as to whether these different carbocations are actually rearranged structures or whether this is an example of resonance. And what we mean by that is you've heard of carbocation rearrangement before, where, say, you can rearrange from a regular carbocation through some kind of transition state to another carbocation, right? We've seen, for example, it's known that ethyl cation rearranges to switch which of your two carbons actually has the positive charge. And the question is, and these carbocations that I've drawn are called carbenium ions. Carbenium ions are classical carbocations, 3 bonds and an empty p orbital on a carbon. But it's also thought that perhaps, and if you were to ask what does that transition state look like, you might draw a structure like this where you have a hydrogen and it's halfway between the two carbons. You got one bond sort of broken and the other bond sort of formed. It's almost like you have 3 atoms sharing 2 electrons. And the question is that a transition state or is it actually an intermediate? You could imagine a picture where you have the and carbocations with a sort of 3-centered 2-electron kind of bond are called carbonium ions. And so the question is, are these different structures of a carbocation intermediates? Are they more, if they're intermediates, are they more or less stable than the possible potential carbonium ion? Is the carbonium ion an intermediate or a transition state? And the answer really is it depends. In some ways, you can represent the structure of cyclopropyl carbinol with, let's see, we can take our initial structure for cyclopropyl carbinol and you can draw it as though it were a hybrid structure where you've got partial bonding character here, partial bonding character here, and then partial double bond character there with a positive charge delocalized. And so the key question is, are these in equilibrium or is this an example of resonance? And it might seem like a subtle point, and in fact it is, because the potential energy landscape of a lot of carbocations is relatively flat, meaning there's not a huge difference between the transition states and the intermediates. And so this was a very huge argument in physical organic chemistry about 50 years ago, and people got angry, and now we just sort of don't worry about it anymore, other than to recognize that these kinds of things can exist. We'll say more about it next time, But it turns out a cyclopropyl carbinol ion is key in the synthesis of cholesterol, and it's how we take two farnesyl pyrophosphate molecules and we stick them together head to head. So I know that was a little bit abrupt. We'll have more to say about carbocations last time because, as expected, we did not finish Chapter 1 today. So with that, again, we leave you from within the shadows of the everlasting hills. May peace and joy be with you this day and always. We need someone to play As the Dew from Heaven Distilling. All right. Thanks, guys. See you next time.